In this video, we're going to take the principles of beam equilibrium that we discussed in the first two parts of this lecture and apply some math to them and show how we can use these principles to figure out what the reactions need to be. In other words, the forces within a beam's supports that allow it to remain in equilibrium. We'll do this first using some examples just with point loads, and then in the next video, we'll up our game a little bit and talk about distributed loads, how we turn those into point load equivalents, one additional kind of step of complexity. For the moment, we'll stick with fairly simple loads, and we'll stick really with just one. We'll do some examples later on where we look at slightly more complex problems. So to do this, we're going to take a pier, and to motivate ourselves, we're going to imagine that the pier is all that's standing between us and this person eating shark below, right? Good motivation to figure this out. And the loading condition that we are going to want to solve is for a 500-pound load in the middle of a 32-foot span. So this could be a group of people, this could be a whole big barrel of shark chum, this could be any number of things. All we need to know is that it weighs 500 pounds, and we're going to treat it as a point load. That is, it's a small enough load that it's concentrated in something we can think of basically as a single point in the middle of the span. So going back to the last video, what do we need to know? Well, we need to know the loading and the support conditions. For the loads, we need to know the total span, which is given to us as 32 feet, fine. We need to know the position of the loads, and we have dimensions showing that 500-pound load is midway across the span, so 16 feet from either side. And we need to know its magnitude, 500 pounds. Now, we're going to use the position and the magnitude to figure out what that load's moment is on one support or the other. We'll back out of that to figure out what the two support conditions have to be. We do also have to know something about the supports. We have to know where they are. In other words, are they at the end of the span or are they somewhere in the middle? And crucially, we need to know the type of supports. What do I mean by the type of supports? We raised this in the last video, didn't quite address it. Here's where it gets really important. We have three types of connections that we can use to support a beam onto piers or columns or whatever. And these are basically the structural connections that we'll work with in all of our calculations for beams and otherwise. The three types are roller connections, pin connections, and fixed connections. And each one of these types allows us to do different things. If we have a roller connection, seen here in the top, roller connections provide only vertical resistance to loads, so the beam can slide back and forth, left to right. We sometimes see these in highway constructions where we're worried about bridge decks or something expanding. We want to support the loads going across them, but we want the deck to have some freedom to move in and out. Fairly rare, though, in architectural circumstances. Fixed connections, which you see down here, provide vertical, horizontal, and rotational resistance. In other words, they fix the beam horizontally, they fix the beam vertically, so they support it, and they don't allow the beam to rotate around either support. The connections we're going to assume for the most part are what are called pinned connections, and these provide vertical resistance and horizontal resistance. In other words, they keep the beam in translational equilibrium in the x direction, left to right, and the y direction, up and down. But they don't provide any rotational resistance. What do I mean by that? They're not fixed connections that keep the beam from spinning one way or another. They are literal pins that allow the beam to rotate around either support. Why would we use this? Well, there may be conditions that we have to be wary of. The beam may be big enough that it expands and contracts. We don't want it to twist the foundations out of the ground. But there's also a convenience that pin connections give us when we're trying to calculate things. And that is that if they can't absorb any moment, if they can't stop the beam on their own from rotating one direction or the other, then there's something that we know about the beam's, the state of the beam's equilibrium at those conditions. And that is that the sum of all of the moments around either one of the supports always has to equal zero. That's this equilibrium equation here. Sum of the moments around either the left or right support equals zero. When we have a pin connection, usually drawn like this, we can always assume that the sum of all of the loads on that beam, and particularly the moments that they induce around that point, have to equal 0. In other words, the loads and the reactions all have to balance out in terms of the rotation of the beam. Okay, that sounds complex. Let's get into an example and we'll see exactly how this works. So let's take our pier with the shark now removed. We have the 500-pound load that's in the middle of the span. We now know, as you can see here, that the connections are pinned, and they'll be pinned for virtually all of the examples that we do to keep things simple. So what we want to do to find out reaction left and reaction right is to use this principle of the pinned connection, to use the idea of rotational equilibrium about the supports to do a kind of thought experiment and figure out how all the rest of the loads have to balance out. The way to do this is to start by considering all of the loads and reactions acting on the beam and their effect, the moments that they all create around one support or the other. Why do we do this? Well, as you can see, if we think about the sum of all the moments around the right-hand support, we only have 2 possible loads. We have one that we know about, the 500 pounds in the middle of the pier, and we have the other reaction left, we'll call it. The sum of the moment that's induced by the load and that's induced by that left reaction around that support have to equal 0. We want the beam to be in rotational equilibrium. What about the reaction on the right side of the beam? Well, if we're thinking about the effect of all of these through that support point itself, then this reaction has no moment arm, right? It doesn't have any leverage around itself, and therefore we can ignore it when we're trying to think about equilibrium around that point. So we'll end up with 2 loads that we have to consider, one an external load, one a reaction. We know their positions, we know the magnitude of one of them, and what we're going to try to do is to figure out what this load has to be to keep the beam from rotating around that support. So we write it mathematically like this. Sigma means sum, M means moment, R in this case means right support or reaction. So sum of the moments around reaction right equals 0. That's the desirable outcome. So what are those? Well, let's look at all of the loads and reactions that we have on the beam, and let's see if we can figure out what moment they induce around that support. The first one we can think about is reaction left, whatever the load is, or whatever, the reaction is that's supporting the beam on the left-hand side. And we think about both the magnitude of it, which we don't yet know, and the lever arm that it has around the point we're considering. So however big reaction left is, it's going to have a moment arm that is the whole length of the beam, 32 feet. So its total moment around reaction right is going to be whatever its own magnitude is times its moment arm, 32 feet. Okay, that's going to be going in the clockwise direction, and we can pick whether that's positive or negative. In this case, I've said it's positive. So long as we're consistent throughout the problem, it can be either one. And then the other load that's acting on the beam is that 500-pound load at the midspan. So we think about that both in terms of its magnitude, 500 pounds, and the moment arm that it has around the point we're thinking about. So notice that its moment arm is 16 feet. It's at the midspan. So the lever arm, the leverage that it has around the point that we're considering is its distance from that point. So 500-pound magnitude, 16-foot moment arm. And we know that the reaction left times its moment arm minus the 500 pounds times its moment arm, we want all that to be 0. We want these 2 moments to balance out. We don't want our beam to spin around. So we'll do some simple math. First of all, we'll notice that we have a positive and a negative, so we can take the negative term and just flip it over to the other side of the equation. RL times its moment arm equal and opposite to the 500-pound load times its moment arm, 16 feet. We can multiply those 2 together, and we find that the moment that is induced by the 500-pound load around the right-hand reaction is 8,000 foot-pounds. 500 times 16, and then notice the units, feet times pounds. So that is a measure of torque or moment, the force that's twisting around the right-hand support. Now we want to go ahead and figure out exactly what reaction left is, and notice that this is fairly easy to do. The reaction left is going to be in pounds. Its moment arm is in feet. We have foot-pounds here. So we can divide 8,000 foot-pounds by 32 feet and come up with a figure in pounds for reaction left. And this is what that looks like. We take the moment arm basically out of the left side of the equation. We divide the right side of the equation by it. And what we end up with is 8,000 foot-pounds divided by 32 feet. Notice that the feet cancel each other out. 8,000 divided by 32 is 250. So the reaction on the left side of the beam has to be 250 pounds to balance out the moment or the twist or the leverage, whatever you want to call it, of our 500-pound load. So that's reliable. We've mathematically shown that this reaction has to be 250 pounds. Now, we want to also find the other reaction. We might be designing the piers, or as we're going forward, we'll find that finding the reactions is the crucial first step to getting inside the beam and finding out what the internal states of stress are within the beam. So we want to find both reactions. Now, we could go through exactly the same process, solving instead of for the sum of moments around reaction right, summing the moments around reaction left. But we can also solve for the sum of forces in the y direction. We can solve not only for rotational equilibrium, but we can also solve for translational equilibrium. And this is going to be a little bit simpler because we don't have to worry about the positions of the loads if we're solving for the forces in the y direction. All we have to look at is the sum total of loads that are either pushing the beam up or pushing the beam down and figure out a way to get those to zero. So again, we look at all of the forces that are acting on the beam, and we have three of them. We have 250-pound reaction. Notice that that's pushing up. We have a 500-pound load. Note that that's pushing down. And we have an unknown reaction on the right side that we assume, probably, is pushing up. So mathematically, we can write that like this. 250 pounds up minus 500 pounds down plus whatever RR is up. And just like we want our rotational movement to be zero, we want our translational moment to be zero. So sum of all of those forces we want to equal zero. If we do the math very simply, 250 pounds minus 500 pounds, note that we're just in pounds now, so we don't have to worry about dividing out the feet from foot pounds. 250 minus 500 is minus 250. Note that we have a negative here that we can move over to the other side of the equation. We get a very, very simple solution. RR is also equal to, move that over there, 250 pounds. All right. So we have solved for both reactions, and notice a couple things, right? First of all, it's fairly straightforward and intuitively obvious that if we load something in the middle, that load is going to get divided evenly between the two supports. 500 pounds down, 250 pounds on either side pushing up. We could go back and check this. We could say, well, okay, we want to make sure that we're in rotational equilibrium around the left-hand support. 250 pounds times 32 is in fact going to be equal and opposite to 500 pounds times 16. Right? That's exactly the same math that we did to solve for the sum of the moments around the right-hand reaction. So it's a very, very simple, kind of intuitive set of equations here. And we find that that 500-pound load in the midspan gets equally divided among the supports. What happens if we move that load over? Right? What happens if instead of being in the midspan, that 500-pound load is only 8 feet from the edge of the pier? Right? It's asymmetrically loaded. Now, we know a couple of things, right? We know that the sum of the vertical forces, or the vertical reactions, RL and RR, is still going to have to be equal and opposite to those 500 pounds. But now notice that we've changed the position of the load. And so again, let's throw some math at this to see if we can figure out what happens to the reactions, whether the reactions actually change. We'll go through exactly the same sequence. We'll pick one of the supports and we'll solve for rotational equilibrium around that support. So sum of all of the moments around the right-hand support equals 0. Now we have three forces: reaction left, 500-pound load, and reaction right. But notice again that if we're trying to solve for the moments or the leverage around this point, reaction right, no matter what it is going to have a moment arm, a lever arm of 0 feet. And so it's not going to contribute any moment to the equilibrium equation around its own point, basically. So we can do exactly the same thing that we did before. We look at each of the loads and we figure out, first of all, whether we know its magnitude or not. We don't know reaction left's magnitude. That's what we're trying to find out. But we do know its moment arm, and its moment arm has stayed the same. It's still 32 feet, the distance between it and the support that we're doing the equations around. Notice, though, that the 500-pound load still has the same magnitude. We haven't made it any lighter or heavier. But because we've moved it over, it now has a different moment arm. It's 24 feet from the point that we're considering instead of just 16. We still want all of this to be 0. But notice that when we move the 500-pound load over to the other side of the equation and multiply 500 by 24 and pounds times feet, we get a much bigger number. Because we've moved that 500 pounds further, we have greater leverage on reaction right than we did before. Think about this as having the same force but a longer wrench, and you're able to get more torque, more leverage because the moment arm is longer. So notice foot-pounds, we're multiplying pounds and feet, so we get a figure in foot-pounds showing us that we definitely have torque. And now notice that on the left we have the same situation that we had before, the unknown reaction. Its moment arm is still 32, and the reaction, of course, is going to be in pounds. The moment arm is going to be in feet. We have foot-pounds over here. And so the next step is to divide this figure by 32 feet. And what we're basically doing is taking the moment arm that reaction left has around the point we're thinking about, we're taking that out of the moment that is imparted by the 500 pounds. And that's going to tell us how much force RL needs to be to counteract the moment that the 500 pounds is putting around the point we're thinking about. So 12,000 foot-pounds divided by 32. And notice we're going to take the feet out in both cases. We'll be left with a figure in pounds. 12,000 divided by 32 is 375 pounds. All right. Notice that that compares with 250 pounds that we had in the symmetrically loaded example. So as we've moved that 500 pounds closer to the support, we find that that support is beginning to pick up basically more of the load. That because we want the thing to be in rotational equilibrium, this support has to start working harder to counteract the moment, the increasing moment that that 500-pound load is imparting around the point that we're thinking about. Now, once again, we can solve for translational equilibrium. Notice that in this case, we still have 500 pounds going down, but now instead of 250 pounds, we have 375 going up. So 375 going up minus 500 pounds going down. That is going to give us a figure for RR that we'll need to keep the beam in translational equilibrium, to keep it from moving up and down in space. So 375 pounds minus 500 pounds, again, just solving for translation, so no foot-pounds in this case. That gives us minus 125 pounds. If we move that over to the other side of the equation, we find that RR equals 125 pounds. Now, if you're thinking through this intuitively, you can see that there is very definitely a relationship, that because this is now 1/3 of the way across, the relationship between the two reactions is 2/3 and 1/3. This is fairly straightforward math. If you want to push it even further, you could think about what would happen if we put the 500 pounds exactly on to that left support. And what we would get is, again, kind of intuitive. This support would pick up all of the 500-pound weight, and the reaction over on the right would pick up nothing. The reason for that is that the 500 pounds and the 375 pounds would be passing through the same point. There would be no moment that either imparted to that support, and therefore we wouldn't need any force in the right-hand support to counterbalance any moment, right? So the closer that load gets to the support, the more the support is going to pick that up. And as it gets closer and closer and closer, the magnitude of that support is going to grow and grow and grow and grow and grow until when this is actually on top of the support, it will pick up that entire load. This will go from 0 to 500 as we move that load from right to left, getting closer and closer to the support. In the next video, we will do a couple of examples with distributed loads. Same math, but we have an additional step where we have to take a load that is spread out over the beam and think about how to calculate that, what its equivalent would be that will allow us to do some of the same moment equations around the support. And again, looking to find both rotational and translational equilibrium, using those principles to come up with the set of reactions that are required to keep Y and M at 0.